Hello, my name is Clemens. I'm the CTO of Persival, and today I'm going to show you how to effectively transfer data between individual models in a co-simulation. In my last tutorial, I showed you how to set up a co-simulation and how to define a scenario using ASAM Open Drive and Open Scenario. And today we are going to focus on the interface between different models. And we're using the ASAM Open Simulation Interface standard for that, or in short, ASAM OSI. If you remember from my last tutorials, if you don't, then go ahead and rewatch them, or if you missed them, watch my first tutorials. But there we defined a very simple co-simulation architecture using the AVL scenario simulator. And we have here esmini as a scenario player that will read in an open scenario file and play it back during simulation runtime. And then we have a very simple sensor model. It's a sensor model template from OpenMSL, so an open source model. And then we have a recorder that is recording the output of esmini and also the output of the sensor model. And you see here that this is a sensor view output, and this is a sensor data output. But what does that actually mean? Let's go into the Open Simulation Interface documentation for that. ASAM OSI is an open standard. It's an open source standard. It's freely available on GitHub. You can contribute there or write issues there, and there's also where the documentation is hosted, and that's what we have here. For starters, let's look into the architecture of OSI. OSI defines different what's called top-level messages. OSI is based on Google Protocol Buffer. It's a layer on top. And you have several different message types that you can transfer between different models. For example, an environment simulation can output a sensor view. That's what we saw earlier. That's what esmini outputs. You could have an environmental effects model connected there that just puts more effects in the environment. For example, if you want to simulate environmental conditions like rain or fog on top of your general environment simulation, you could have a model there. It has the same output sensor view, and then you can connect a sensor model, or you can directly connect the sensor model to the environment simulation. That doesn't matter because the interface is the same. And you can connect a sensor model with a sensor view input to basically anything that outputs an OSI sensor view. The sensor model itself outputs a sensor data, so it's a different message. It's a different message type. And you can connect several models, logical models, or your functions, your perception stack to that with a sensor data input. There are also other top-level messages, for example, a traffic command or traffic update, where you can interface an environment simulation with a traffic participant model. So for example, with a traffic command, the environment simulation can transmit individual open scenario actions to the traffic participant model that will then execute these actions and give an update to a new position, new orientation, or new state of that traffic participant back to the environment simulation for a closed loop simulation. So there's different varieties and different use cases to use OSI. I will mainly focus on the sensor model use case, so we will be mainly talking about sensor view and the sensor data message. So let's jump into that. Down here in the menu, you will find an Open Simulation Interface, the class definition. So each of these messages are defined as classes in OSI. We're in OSI version 3, so we can go to OSI 3, and then we can look for the sensor view. That's what we are going to start with. And they're called top-level messages because they consist of several other sub-messages. And that you can find here. Every top-level message in OSI has a version and a timestamp. You have other definitions like the sensor ID, you have a mounting position of a sensor. You have your host vehicle data, so the current state of your ego or host vehicle. The one that's mainly used, or that one that has the most information, is the ground truth. So let's jump into that. And the ground truth transmits basically every state of every object, moving or stationary, at a current time during the simulation. So in every step of the simulation, you can transmit with this SensorView ground truth interface of OSI where objects are, what orientation they're in, and going down to a very low level of detail. One example is moving objects. So we've simulated scenarios before where we have different vehicles going on different lanes in different directions. And that you can transmit as a moving object. It's a repeated field, so it's basically an array of every moving object in the scenario. And for every moving object in the scenario, you can define different parameters. First of all, it has an ID, and then we have this base. And the base contains the basic state of an object. It's a dimension. You can transmit the position in global coordinates. So this is in the global, on the map, on your road network, in that global coordinates. You have the position, you have orientation, you have velocity, acceleration, and so on. In OSI, we have different coordinate systems. When we talk about objects, it's always the center of the bounding box. So you see here the ground truth, that's the world coordinate system, and we have the center of a bounding box of this moving object. And also the ego vehicle is a moving object. So everything that moves in the simulation is a moving object. And then we can go more into detail. If the moving object is a vehicle, we have dedicated vehicle attributes. For example, we have information about the wheels, what radius we have on the wheels, the number of wheels. We have the axle positions, so the rear axle, the front axle, where they are with respect to the center of the bounding box. And we've also more detailed wheel data, like positions of individual wheels, where you can simulate also the vehicle dynamics or the reaction of the wheels to the road, the suspension, also the steering motion, the rotation of the wheel. All of that can be transferred with with OSI, with this interface. Of course, we not only have vehicles, we might have other moving objects, for example, pedestrians. So also for pedestrians, you can say, first of all, where's the route? So where's basically the lowest point of the pedestrian? And then we can actually transfer individual bones. So if the pedestrian is moving its arms and legs, we can transmit this via OSI between the environment simulation and, for example, a sensor model to accurately represent also pedestrian movements in a sensor model. Similarly to moving objects, we have stationary objects. We can also define them. This is basically everything that stays the same, stays in one position during the simulation, except traffic signs and traffic lights. Those are separate fields, separate messages. With them you can transfer between the environment simulation and, for example, a sensor model or a behavior model, the state or the current state of traffic lights. If it's green, if it's red, so if it's stop or go. You can also transmit the lanes. So if you have a lane keeping algorithm you want to test, you can see if it stays in one lane. You can transfer environmental conditions like rain intensities, fog, between the environment simulation and a sensor model or any other connected model. And that's a quick introduction into the SensorView message. There's lots more to explore, but let's actually now jump over to the sensor data. So SensorView again transmit current states of the simulation from the environment simulation to a sensor model, and the sensor data message is the output of the sensor model. So let's go to the sensor data message. Again, like every top level message has a version and a timestamp. Furthermore, we have sensor ID, we have mounting position, and so on. It can also contain the sensor view. So to keep track of the ground truth and what's actually happening in the scenario, you can basically copy the input of a sensor model in here to the sensor data. So subsequent models can also access that and see what's going on in the ground truth. And then we have detected entities. So if you have an object model, so a sensor model that detects objects and that outputs an object list of objects in the scene that it detected, you can use detected stationary object, detected moving objects, also detected traffic lights. So you can output which of the objects in the ground truth you have detected, and not only which one, so it's not just a selection, it's an actual new definition of the object, because a sensor might perceive an object differently than it actually is. So you can set a different position, orientation, or different dimension. Maybe you only see a car from a certain angle, so you don't see the entire dimension of that object, and you can put that here. So you can freely define how that sensor perceives that object as it is modeled. Apart from object detection, that's one output. So you have an object list as an output, but you can also output what's called a feature data. And feature data is depends on the sensor technology. So you have radar detections, LiDAR detection, ultrasonic and camera detections. And with this interface, you can output individual detection points. So individual radar detections or individual LiDAR detections. And for LiDAR, this is what's typically referred to as a point cloud. So you have individual detection points that form a point cloud. So this is a repeated field, and you have an array of LiDAR detections in this case. And here again, you can set a positions where the detection is. In this case, it's in the local coordinate system of the sensor, because that's what your real sensor would also typically output in your real system. So this is in spherical coordinates in the sensor coordinate system, like you would have on a real LiDAR. You can set intensity per points, reflectivity, and so on, depending on your LiDAR. So the sensor data can contain the ground truth, so the input, and then we have basically two output formats, either detected objects, so an object list, or the feature data where you have individual detection points. And that's, in a nutshell, how you interface between different models. How you use this data is completely up to you. You can have very simple sensor models like we had before, or very complex one that use this data to build up all 3D world, that do ray tracing, then output point clouds. All of that is possible using the ASAM OSI interface. If you have any more questions about OSI, feel free to leave a comment below. And in my next tutorial, I will also talk about OSI, but not as an interface format, but actually as a format to store data, because OSI can also be used for that. That I will cover in my next tutorial. So stay tuned for that.